Ryan is Senior Manager of Engineering at Sproul and manages Sproul's Denver office. She has 15 years oil and gas industry experience with positions at Woodside Energy, Aero Energy, MHA Petroleum Consultants, all prior to her position now at Sproul. Her experience includes reserve and contingent resource evaluations and audits, U.S. and international fair market evaluations, and expert witness testimony, and she teaches classes for PetroSkills as well. She has been named to a whole bunch of positions, to a whole bunch of societies. Just last year, she was named by the Denver Business Journal as one of the 40 top women in energy, received the 2019 SPE Rocky Mountain Service Award, and she is a registered professional engineer in Colorado. So, without any further ado, I will hand it over to Ms. Deb Ryan.
Well, thank you, Clay, for the introduction, and welcome everybody. Really glad that you could join us for the discussion this morning about an overview of black oil PVT. So, what we're going to go through today is we want everyone to kind of leave here today with an overview and a knowledge of some of the different reservoir fluids and what some of those mean and how they change, how these fluids change with temperature and pressure. So PVT being pressure, volume, temperature relationships for our reservoir fluids. We're going to talk a little bit about some of the black oil correlations that we can use to characterize our fluids once we know what kind of fluid we have. And we're also going to talk a little bit about some of the lab tests that can be done in order to also characterize the behavior of those fluids in the subsurface. So, why are our fluid properties important? First of all, we need to understand what kind of fluid we have in the ground so that we can estimate the volume of hydrocarbons, oil and gas in the ground. And then we also need to be able to understand it so that we can look at what our reserves and resource evaluations look like, what that recoverable component looks like for gas, for condensates, for volatile oils, and for black oils. And to do that, we really have to be able to define and describe the reservoir process that the fluids undergo as we deplete our reservoirs so that we can actually predict our reservoir behavior. So this is going to be, we're going to talk a lot today about phase change and what that does both in the subsurface and when we bring those fluids to surface through our facilities. And also if we're going to be then implementing any enhanced oil recovery or EOR methods and how those are going to impact the fluids in the ground. We need to be able to calculate well inflow performance descriptions for how the fluid is going to flow into our wells, up through the wells, and like I said, through our surface facilities. How much free gas are we going to get coming out of our black oils, which needs to be understood so that we can understand pipeline sizing and sales contracts. And we also need to understand if there's any wax or asphaltene issues that are going to occur. We're not going to talk about this so much today, but it's just something to be aware of, particularly for those of you who work in the surface and facilities, that we need to be able to understand if we're going to have these kinds of processing issues at surface, and they're things that we need to test for very early. And then the other aspect of our fluids that are really important is, at the end of the day, we're trying to sell these products. And so we need to be able to characterize what that's going to look like, because different products will get different pricing depending on what kind of processing or whether there's any impurities in our gases and our oils and that kind of stuff. So it's really important for the marketing team within our companies to actually understand what kind of price we can get for the final sales product. So here we've got some typical hydrocarbon mixtures from different parts of the world. The first one that I'm going to point out here is a sour gas. Very dry, so almost predominantly methane, essentially in our reservoir component. A little bit of nitrogen in this one, not such a big deal, but just a pain to have to process out. Interestingly here, a lot of H2S and a lot of CO2. So the H2S being the bit that makes this sour, but obviously has very, very bad health implications, if it comes to surface in terms of the kind of equipment and how we actually have to process this gas, which adds costs. And then high CO2, which both, if from an environmental point of view, we also don't want to be putting out in the atmosphere, but also if there's any water in this system, when it mixes with CO2, forms carbonic acid, it can be highly corrosive for our downhole and surface equipment. So again, hugely important that the people designing our equipment understand these impurities because of those integrity issues. And then interestingly, and one of the things I wanted to point out, this particular gas has a little bit of helium in it. And I don't know if anyone has worked on much helium projects, but here in the US, we have a lot of the world's production of helium, and helium is actually really valuable. So even in really small quantities, helium can be a worthwhile component to strip out of your gases if it's something that's actually or something that actually appears in your gas stream. As we move then from a dry gas, where we're predominantly methane, into what we call a gas condensate. Still very predominantly methane, but we're starting to see some of the other components. So our ethane, propane, butane, pentane, heptane, and our C7 plus components. You can see, interestingly, in our gas condensate, there isn't very much C7 plus. So essentially everything from that heptane and above just lumped together. And that's actually, we're going to talk on the next slide a little bit in terms of how we can start to categorize and identify some of these. And the C7 plus component is one of the ways that we can actually start to understand whether there's the difference between a gas condensate and a volatile oil, or our gases and our oils. Still a little bit of CO2 in this one that might need to be processed out, which is really important to understand. As we move then from our gas condensate into our volatile oil, you can see we've still got predominantly, methane is still the most common element in this particular gas, but it's much less quantity than we saw in that gas condensate. And then starting to see a much higher quantity of the C2 to C6 components that are, once we put them into surface conditions, some of these are going to distill out, sorry, my keyboard's being very volatile. Some of these are going to distill out as liquids when we sell them, or are going to get processed as natural gas or NGLs as well out of that. And it's starting to see an increasing amount of that C7 plus. And then when we go to a black oil, interestingly, this particular black oil has more methane in it than the volatile oil piece, which is why sometimes that methane component isn't necessarily the best judge of whether it's a volatile oil or a black oil. And we're going to talk a little bit later about why that's important. But you can see here, this C7 plus is a lot higher. So we're starting to see a lot more of those heavier ends in this particular fluid. So we can get all sorts of different compositions. Every single oil I've ever looked at is different. And it can give us some indication of what kind of fluid we have. But again, not always. So in this particular instance where the C1 is higher, but can also then tell us about some of the other processing issues and equipment we might need to consider when we're actually dealing with this particular hydrocarbon. So how do we start to classify some of the things? So I've already started to use some of the different types of language in terms of a dry gas, a wet gas, a gas condensate, a volatile oil, an intermediate oil, and then a black oil. And there's three kind of things that, you know, in lieu of any other information about your reservoir, we can start to, or your reservoir fluid, I should say, we can start to characterize and understand where we are in the spectrum from dry gas to black oil. The first is the initial gas-oil ratio. And I say initial, we're going to talk about phase behavior and how gas-oil ratio changes with time as we get below our bubble points. But initially for our dry gases, we're essentially 100% gas. There's no liquids in those dry gases from our reservoir production stream. And like we saw with that dry gas example, very small percentages of that C7 plus component. As we move down through our wet gases, we're starting to see this gas-oil ratio starting to drop. And really for when we're looking at some of this stuff, particularly in our unconventionals here in the US, where we don't tend to get as many downhole fluid samples of that initial fluid, being able to characterize that initial gas-oil ratio that we are producing and the difference between here, these gas condensates versus the volatile oil. And here as well, the difference between the C7 plus component in that reservoir fluid is one of the things that can be a really big determinant in terms of whether this is originally a gas in the reservoir and it's going to drop condensate out of it, or if it's an oil initially, it's going to have gas liberated out of it. Interestingly for these two, which is why it's often very challenging for us to differentiate, the API, so the stock tank density of these fluids is almost identical in terms of the range. It covers almost a full spectrum of potential APIs. So API, even though it's something that we often talk about in terms of our fluid, this is a 35-degree API oil. This is a 42-degree API oil, a 50-degree API oil on its own as a piece of information isn't necessarily going to allow us to understand the difference between some of these volatile fluids and even potentially a black oil in terms of how that fluid's going to behave in the reservoir over time. I love this picture. So this particular, one of the other things we need to understand when we're looking at the reservoir fluid is that reservoir fluids can actually change and be different even within a reservoir. So this particular picture is from a field in Wyoming. The actual field has a vertical thickness of about 1,000 feet. So it's a really, really thick reservoir package. And what we can see is at the very top of the reservoir, when the fluids were sampled, this is the original before any production, we have a very, very light condensate that's coming out of the gas. And as we move in depth, because of the density variation throughout this reservoir, because of that very, very gross thick column, density allows the PVT to settle. And as we move down through the reservoir, we move through these different phases of very lean condensate out of our gas, out of our gases, coming down to more of a volatile oil component into something that's starting to behave more like a black oil, and potentially then actually an oil rim right above the oil water contact. So even within our reservoirs, understanding vertical difference and vertical separation in terms of how we manage these reservoirs and how we produce these reservoirs is really important, because if we're a gas reservoir and we want to maximize liquids, we have to produce our reservoirs in a certain way. If we're an oil reservoir and we're trying to minimize how much gas we produce, we have to produce our reservoirs in a certain way. Or if we're actually chasing the gas and we're not so worried about the liquids, we control our reservoirs in different ways. So this is a really important thing to understand as we're doing that original reservoir characterization and understanding the reservoir performance with time. So how do we start to do some of that? As I mentioned, PVT stands for pressure, volume, temperature. And so this particular slide is looking at just the temperature and pressure variations when we have a constant volume. We could do these in different, we could do volume temperature with constant pressure, and we look at advice for all these different combinations, but the ones that we're looking at for reservoir fluids, we tend to look at pressure versus temperature and constant volume. For this particular phase behavior curve, phase diagram, this is an equal parts of ethane and N-heptane, so our C2 and our C7. And what we're looking at is when we mix this fluid, at some point we have our critical point, where the fluid doesn't know if it's an oil, doesn't know if it's a gas, it's kind of just a mishmash. So this critical point is really important with our fluids, with when it is in that critical point. Everything above in temperature is going to be a gas. Everything below that critical point is going to be a liquid when we're outside of this two-phase region. When we start to then, for our, depending on where we are in terms of our reservoir temperature, as we drop our pressure, which we do through production, once we either, if we're on this side and we're gas initially, once we drop down and we hit this pressure, we hit what we call our dew point. The point at which the first drop of liquid, the first drop of dew, forms in that gas and starts to drop out as a liquid. And as we move down through this two-phase region, we get increasingly more oil and less gas in that mixture. If our initial reservoir pressure is over and temperature is over here, we're initially a liquid, so we're an oil. And again, we're 100% oil until we drop down and hit our bubble point, which is the temperature and pressure for that particular oil, at which the very first bubble of gas appears in that liquid. And again, as we continue to move down through this two-phase region, we get more gas coming out as we continue to deplete our reservoir pressure. So it's really important to understand where we sit on this phase diagram in terms of the type of liquid and the type of fluid we have in our reservoir. So, and I know this is really busy, but we're going to spend a little bit of time here. So when we look at different fluids, so I talked about with that, in that first table we had from dry gases to wet gas, gas condensate, volatile oil, and our black oil. So if this is our original reservoir condition, so we're sitting at something like 120 degrees Celsius, and our original reservoir pressure, this chart's in MPa, which I know we often deal in PSI, but we're in MPa here, just over 45 MPa. So the other thing that we need to note is what our separator conditions are. So here is our separator conditions at 50 degrees Celsius and not quite atmospheric, but something just above atmospheric. And understanding how we're going to operate our separators is really important in terms of the conditions and where we sit in how the fluid is going to behave. So initially, let's start with our dry gas. You can see for each of these, the critical point is essentially indicated on the phase diagram chart. So for our dry gas, over down here in the corner, you can see from our initial reservoir conditions, reservoir temperature and pressure, and again, assuming a constant volume, is that as we continue to deplete and produce our reservoir, we never get anywhere near this dry gas window. So we stay as a gas throughout the entire life of the reservoir at reservoir temperature and pressure. When we start to then bring that gas to surface, you can see even our separator conditions are still outside our two-phase window for our dry gas. So in our separator, we're also still 100% gas with no liquids dropping out in our separator. So gases are easy in terms of trying to manage reservoir. To get maximum recovery, we want to be able to drop that reservoir pressure as low as we possibly can to maximize recovery in terms of reservoir management. When we then move to our wet gas, so now we're actually adding some ethane and propane, but still not really much of that C7 plus into our reservoir fluid. Again, here's our initial reservoir temperature and pressure. And as we deplete our reservoir, the fluid that's coming to surface, again, is still 100% gas. We're still a long way from our critical point on our wet gas and a long way from this two-phase window where we're going to hit the dew point. Interestingly, though, with a wet gas, when we bring that gas to surface, our separator conditions are now within that two-phase window. So we're going to actually get liquids out of our separator, even though the production coming out of the reservoir is still going to be 100% gas. We're not going to go through that today, but there's then corrections that your reservoir engineer can make for a wet gas fluid, because you've got to understand in the reservoir, we've got to put that liquid back into our characterization of our fluid, our gas, so that we can actually make sure that those heavier components are being characterized correctly. But today we're going to talk about oils, so we're not going to go through those equations. As we then move out of our wet gas and into our gas condensate, you can see over here, here's our critical point for our gas condensate. So because our reservoir temperature and pressure are on the right-hand side of our critical point, initially at reservoir conditions, we're gas. So, and as we produce our reservoir and we drop our reservoir pressure, we hit our dew point. And we continue, as we continue to drop down through that two-phase window, what we start to see now is that there is more and more liquid that is going to be coming out of our gas. And what we need to understand is that is happening now in the reservoir at reservoir temperature conditions, reservoir temperature pressure conditions. And we get, if you work in a gas condensate reservoir, you'll often hear the word condensate banking. And what this is around that near wellbore region, around our well, where in the reservoir we are dropping below our dew point, we are starting to drop that liquid out, and we're not going to bring it to surface. So reservoir management in these gas condensate reservoirs, we really need to understand what are we maximizing. Because if we want to maximize our liquids, we want to try and stay above that dew point in our reservoir in order to actually bring those liquids to surface so that we can have them drop out in a separator, rather than if we drop below dew point in the reservoir, having them dropping out in the reservoir. So it's really important to understand that. When we then flip to our volatile oil window, we can see, given that gas condensates and volatile oils have often very similar compositions, the phase behavior and the shape of this phase envelope is actually quite similar. The difference being, though, is that our critical point for our volatile oil is over here. And so because our initial reservoir temperature and pressure are on the left-hand side of our critical point, initially we are now an oil, not a gas. The same rules apply, though, as we drop down our reservoir pressure and then we hit now our bubble point and we start to bubble gas out. What we're doing is we're bubbling gas out in the reservoir before we then bring it to surface, and we'll have more and more of that gas coming out. But it's very interesting and important to note that, again, as we start to bubble that gas out in the reservoir, gas actually moves through our reservoirs much easier than oil does. And again, we're not going to go into some of those that methodology or mechanisms today, but that's where we'll often see our gas-oil ratio increasing with time, because what we're doing is, as we're dropping that gas out and the gas is coming out of that oil, The oil's getting heavier and heavier because the light ends are coming out of it, and we're going to show you some of these characterization pieces in a little bit. And that gas is going to continue to increase and flow to our wells, preferentially to oil. So reservoir management of gas condensate and volatile oil reservoirs is extremely critical in understanding what the saturation pressure is, so the dew point for condensates and the bubble point for volatile oils. And we also need to understand what is the main product that we're trying to optimize with our reservoir management plan. Is it gas? Is it oil? Are we trying to do both? How are we trying to maximize what we're going to get out of this reservoir? And then what we're going to talk about today, predominantly, is our black oil. So you can see over here, the black oil has a critical point over here, and our reservoir conditions are much lower than this critical point. So we're in oil initially. Because our reservoir conditions, our initial reservoir temperature and pressure, are so far above the bubble point, we're in what's called an undersaturated reservoir. And so there is no gas cap, because all of that gas that's sitting in that reservoir is in solution. It's not until we drop the reservoir temperature and pressure down far enough that we hit our bubble point that we'll start to actually have gas coming out of solution to have free gas in our reservoir. So something that we need to be really careful with the characterization of our black oil reservoirs is that if we find a reservoir that has a gas cap over an oil, it means that initially our reservoir pressure is at bubble point pressure. Because in order to have that equilibrium of gas and oil in the reservoir at the same time, we need to be we cannot be above that bubble point, because otherwise all of that gas would still be sitting in the oil. So it's something when we're QCing lab reports, and we're not going to talk about how we actually QC lab reports today, it's something that's really important in terms of our understanding of the original reservoir pressure relative to the bubble point pressure in our reservoirs, particularly, like I said, when we find them with gas caps already present at initial conditions.
Hey, Deb.
Yeah.
A quick question before you move off that phase diagram.
I know this is a lot, yeah.
We had a question come in asking if you could explain how the curve on the phase diagram is determined for the fluid, and the same question for determining the critical point.
So, yeah, that's a great question. Because we've seen, just in that 4 examples of the different compositions, every single fluid is going to have a different phase diagram. If we were back in our equal parts ethane and heptane, some of these kind of tests have been done in the lab where there are known quantities of and being able to control the shape of these. But for our fluids in our reservoirs, because every single reservoir is unique, every single reservoir is going to have a different phase diagram with time. With the fluid, and actually as you change the reservoir properties with time, the phase diagrams are going to shift a little bit as well. So I know that doesn't necessarily help with the answer on that in terms of how they do it, but it's also one of the reasons, and I stress this, that it's so important for us to get lab work done, for us to get samples of our actual oil and understand how it's going to change and behave as we change the reservoir temperature and pressure in our reservoirs, and how we can then optimize our performance. But they are unique for every single reservoir fluid. So, okay. So I've talked about a couple of key terms that we're just going to kind of elaborate on a little bit, because for those of you that have worked with reservoir engineers, or if you're early in your reservoir engineering career, you'll know that there is a lot of nomenclature within reservoir engineering, and it's sometimes a little bit confusing. So there's 3 really key properties, and I'm going to show you what some properties with time look like for these 3 here in a little bit once we've been through the definitions. The first thing we're going to talk about is formation volume factor. So what this is it's a ratio of the reservoir volume that's under temperature and pressure compared to that surface volume, or that stock tank barrel, stock tank surface volume. Because what happens, if you think about in terms of a balloon, under temperature and pressure, when we squeeze that gas, we can get that gas pretty small. But when we actually bring it to surface and take that temperature and pressure off, it expands. And so formation volume factor is accounting for that expansion in our fluids. In reservoir engineering terminology, it's denoted with a B, and if it's oil, it's going to be B with a little subscript O. If it's gas, it's going to be a subscript G, and if it's water, it's going to be a subscript B. So formation volume factor is the first one. We've already talked about gas-oil ratio. From a reservoir characterization point of view, the thing we're really interested in is what is that dissolved gas-oil ratio? What is that initial gas-oil ratio in our reservoir where it's a volume of gas dissolved in a volume of liquid? And these are done at surface conditions. So it'll be standard cubic feet of gas per stock tank barrel of oil. If you've got a gas condensate and it's a condensate, then it'll be the dissolved condensate gas ratio, and it'll just be the volume of liquid in the gas. But we're talking about black oils today, so it's our gas ratio. And these are defined with R. So for our dissolved gas oil ratio in our black oil reservoirs, it's going to be R sub S. And viscosity. Viscosity is really important to understand how these fluids then are going to flow through our reservoir. We're going to talk a little bit about this when we look at the plot, but it's really important to understand this. It's because it's part of our fluid flow equations. Viscosity and formation volume factor are both components that are included in Darcy's equation. So understanding them and understanding how that reservoir fluid is going to then translate to surface volumes impacts our fluid flow. And so it's really important to characterize these and understand these correctly. The other things we've talked about, density. Density is mass per volume, and there's a lot of different ways of calculating density, describing density. So we have kilograms per meters cubed, grams per cc, and then we also talked about API earlier, is also just a density value that can be converted back into some of these other units. For our reservoir properties, we really want to understand what the reservoir fluid density is. And particularly for that example that I showed earlier, density can then impact gravity segregation through our reservoirs. It's why we find gas on top of oil, on top of water, because of density over time. Compressibility is really important. The change of volume per unit of pressure. So again, that gas under really, really high temperature and pressure has a really high compressibility because of how much it can then expand at different temperatures and pressures. Something like water is fairly incompressible, depending on how much dissolved gas is in it. We don't tend to see much compressibility change for our waters. So that's also really important in terms of understanding what the change in pressure and volume is going to be, what the change in volume is going to be in our reservoirs and in our reservoir fluids as we deplete and change those reservoirs with pressure and as we move liquids from reservoir pressure to surface pressure. And then we've talked about bubble point pressure and dew point pressure. So bubble point pressure is that saturation pressure where that first drop of gas starts coming out of our liquid. And dew point pressure is the saturation pressure where that first drop of liquid or that first drop of dew starts condensing out of our gases. So, formation volume factor. So what we're looking at here is formation volume factor versus pressure, where initially, this is our initial pressure, our bubble point pressure, and then just our pressure as we're producing our reservoir. Then on the y-axis, here is our initial formation volume factor of oil. So formation volume factor of oil, BO, and then the I. The formation volume factor at the bubble point, and then again our formation volume factor at our producing pressure, P1. Interestingly, what we can see is how the volume of the fluid in the reservoir relative to the surface volume changes as we change the pressure. Initially, this formation volume factor is actually lower than it is when we hit our bubble point. And the reason for this is that as we start to, and the degree of how much this changes really depends on how much gas is dissolved in that oil. But what is happening is, if you remember, above our bubble point, no gas actually comes out of our oil. So as we're dropping our pressure from the initial reservoir pressure down to the bubble point, that gas that is dissolved in the oil. It hasn't come out, but what it's doing is it's still getting bigger. So it's still expanding, and it's expanding, and it's expanding. And what that's doing is that it's increasing the volume of the oil until we hit the bubble point. And then what's happening is that all of that gas that's expanded in the oil, now as we drop below our bubble point, is allowed to come out of the oil. And it separates now into two phases. So our oil, our remaining oil now has a smaller volume again. So again, depending on how much gas is dissolved in that oil, so for volatile fluids, this can be quite a significant volume change. And again, it's something as we're looking at rate calculations and surface volumes that we need to understand over time. So our solution gas oil ratio, that initial dissolved GOR, again, we've got the same kind of pressure along the bottom. So our initial pressure, our bubble point pressure, and a pressure, just producing pressure with time. And on the left-hand, the y-axis here is our dissolved gas oil ratio, the R of S. What you can see here is above our bubble point, that solution GOR is constant with time. What we know, and we see this from production data, when we are producing our oil reservoirs above bubble point, that producing GOR stays constant because we're pulling our reservoir fluids out as a liquid, and it's not until we get that liquid into the separator that we separate out the gas and the oil. What happens though when we hit our bubble point is that that gas starts to liberate, it starts to bubble out of our oil, and what happens in the reservoir is that the remaining oil has less gas in it. And as we continue to deplete, and as all those lighter ethane and methane, all those lighter ends bubble out of our oil, the oil has less and less dissolved gas in it with time. So the GOR for our fluid, or the solution gas oil ratio, decreases with time in our reservoir fluid. And then the third component that's really important, because again, it's part of our Darcy equation flow calculation, is viscosity. Again, we have now the same three: initial pressure, bubble point pressure, and producing pressure, and the resulting oil viscosities in centipoise on the y-axis. So the change in viscosity here, and we have to remember that this high viscosity is bad and low viscosity is good in this particular case. So it's an inverse from that formation volume factor. But like our formation volume factor, because as we drop our initial pressure down to our bubble point, that gas is taking up a bigger volume and gas is a little bit more fluid, the viscosity actually improves as we move towards our bubble points. But like the dissolved gas oil ratio, once we hit that bubble point and the gas starts coming out, what the oil that is left behind in our reservoir has less and less light ends in it and more of the heavier oils that don't flow as well as some of the lighter oils. Lighter components in our fluid, And so what we see is this viscosity increasing with time. And again, this is really important to understand how that reservoir fluid is going to change with time so that we can actually understand the impact it's going to have on our flow equation. Interestingly as well is that viscosity is, when we look at correlations versus lab data for viscosity, oil correlations for viscosity can have an order of magnitude of double or half, and I've seen it time and time again. And if you think about it, if you're calculating from correlations your oil viscosity, because you don't have any lab tests, which is often the case, but you might calculate with one correlation a viscosity of, say, 1 centipoise, but with another one, I've seen one project that I'm working on at the moment, when we use a different one, we actually get 5 centipoise for everything else the same. The only difference is the correlation we're using. And if you think about that in terms of Darcy's equation and how that oil is going to flow through the reservoir, it has really big impacts to what kind of deliverability and what kind of forecasts we're going to get. So wherever possible, making sure that we include viscosity in our lab tests is hugely critical to make sure the characterization of it's correct for our black oils, because the correlations can be very incorrect when we calculate them. So this is a diagram then of those surface the reservoir volumes and what happens when we take them to surface. And one of the reasons that working with our subsea engineers, our surface and facilities engineers is so important in terms of what kind of volumes we're expecting from surface. So here's our reservoir, and then here's the surface facility. And what's happening here, we're in meters cubed, so, but we could sub this out for feet cubed or barrels or whatever we want to do, but we're meters cubed to meters cubed. Down the bottom here for our water, our formation volume of water, which is for the most part usually 1, because water is fairly incompressible. Usually 1 meter cubed or 1 barrel of water in the reservoir is close to 1 barrel of water or 1 meters cubed of water at surface. So you can see here the volume change in water from reservoir to surface is essentially constant. When we then come in to look at our oil, so B sub O, the volume of oil in the reservoir, once we have dropped below bubble point, actually when we bring that volume of oil to surface, decreases. Why? Because in the reservoir, a lot of the volume that is in that oil is actually produced as gas because we've dropped below bubble point at surface. So you can see that additional oil volume here is now sitting in the gas stream from our dissolved GOR, and that will change over time as we saw from our RS versus pressure plot that we had. But the actual volume of oil itself will shrink. And depending on how much dissolved gas you have, the more volatile this fluid is, the more dissolved gas you have in that fluid, the bigger the impact of that shrink is to surface. So that's something that we always need to consider. And then when we have a gas cap sitting on top of our fluid, or if we've dropped below bubble point and we now have free gas in our reservoir, when we bring that gas to surface, again, once we take that pressure off it, that gas expands. And so you can see this small volume of free gas actually expands to be a much larger volume of gas at surface. And our producing gas oil ratio is actually a combination of the dissolved gas oil ratio plus the produced gas. And it's one of the reasons when we're looking at production data, we have to be really careful that if we're using production data to characterize our fluids, that we're making sure we do it at the beginning of production. So before we have free gas in the system, before we've dropped below bubble point, because in order to characterize what that dissolved GOR looks like at the beginning, so that we can understand how this fluid's going to behave, we need to make sure that it's before that gas oil ratio, before we've dropped below bubble point, that gas oil ratio is increasing because of all the free gas. The other aspect of this is that we need to be able to go and talk to our facilities engineers in terms of the amount of gas processing we need, the amount of oil processing we need, and the amount of water processing we need, and the volumes that we're going to require over time to process how these fluids are going to change with time as we deplete our reservoirs. So, PVT properties and correlations. I'm just checking our time. Okay, I know we're coming up to 40 minutes here, so we're nearly there. So, because of the importance then of our oil formation volume factor, the BO, that initial dissolved GOR, or our solution gas oil ratio, and the viscosity, as I mentioned, there's two ways that we can calculate these for our fluids to understand that characterization. The first is from correlations, or we can actually collect samples and do some lab work. For our oil correlations, there's a couple of inputs that we need, and these are usually things that are available to us. I talked about the API oil, and this is of our stock tank oil that we've collected. That initial solution gas oil ratio, which we can get from our early production data before we're starting to see that free gas impacting and increasing gas with time. We need to understand our reservoir temperature, because obviously our PVT correlations are very dependent on that initial reservoir temperature. And we need to understand something about the separator gas gravity and the separator temperature and pressure, because we saw how important that was with where our separator conditions were on our phase diagrams. And once we have those four things, we can use a number of different correlations to calculate what those black oil behaviors of our formation volume factor our compressibility, our gas-oil ratio, and our viscosity look like with time. And depending on what kind of fluid you have, depending on where in the world your assets are and you're producing from, there's lots of different correlations available in the literature. But it's really important to understand what your fluid looks like relative to the correlations and what the correlations were initially developed for. So standing, for instance, which has been one of the most common correlations that's built into a lot of our PVT software for us so that we don't have to go through the process of calculating the correlations by hand. But standing correlation was initially developed for heavy Californian oils. So if you're using standing to then calculate properties for a volatile oil, you may end up with very different results than what the actual, or very different results from what a lab data would give you for that volatile fluid. So if you don't have lab data, it's often worth testing a number of different correlations to look at the impact that the different correlations have on your properties. And like I mentioned, viscosity in particular is notoriously bad in terms of estimating viscosity behavior without having lab data. So it's something that just to be very cautioned on. So for our fluid sampling, if we're actually going to go and collect those samples and put together a program, we want to make sure we're getting representative fluid samples, which for a lot of time means that we're doing fluid samples as early as possible in field life and before we've started production. So early appraisal wells will often include the ability for us to go and collect downhole fluid samples or separator samples. We're going to talk about the pros and cons of both. And what you don't want to do is you don't want to mix too many objectives into one well test. So if you're going to collect fluid samples and we're doing well tests and we're testing different zones and we're trying to do interference tests, often we can actually mix the results and end up not getting any good information. Instead of, we understand that the fluid is the most important unknown that we have, so we're going to do the best that we can to get the best fluid information from this particular well. So we want to make sure that whatever our main uncertainty is in terms of our fluid description is the thing that we're actually designing our testing and our sampling around. The other thing, particularly for wells that are appraisal wells that haven't been produced, so we don't have the ability to flow them back to large infrastructure because maybe that's not available yet, we still want to make sure that we can condition the well a little bit so that we're not just sampling mud filtrate, because that can lead to very expensive tests, very expensive sampling programs, sorry, for not actually much benefit in terms of the samples that we've collected. So working with the operations team to make sure that the well is conditioned and that the sampling program is set out with the right objectives and that everybody is on board with what the objectives are so that we can collect the best data and the best samples for our reservoir characterization is absolutely key. So for well selection, we want early in well life, usually before production data if possible. We want wells that are going to actually flow almost on their own and stuff like that have a high PI. We don't want to draw our reservoirs down below their saturation point, below the dew point or below the bubble point, because in order to collect a sample, because we want to make sure we're collecting a sample of a single phase fluid. Because as soon as, if we draw the well down too hard, what we end up doing is we collect two-phase fluids, and that can mess up. If we don't know that we've done that, that can mess up our analysis and our lab testing because the fluid is actually not representative of that initial reservoir fluid. And if we think that we've got variation, then we want to get samples maybe by depth, by area, in different fault blocks to make sure that we can characterize how that fluid is changing with time, changing with location, and then how those different locations are going to change with time. We want to clean out any completion fluids on new wells. We want to produce at steady low rates. We don't want that drawdown to be really high because we don't want to drop below that bubble point. As much as possible, we want to avoid that two-phase flow behavior. Sometimes in our volatile fluids, we're really close to that bubble point or dew point, and it can be challenging. So this is why volatile fluids are such a challenge for us to characterize properly. But in our black oil reservoirs, particularly if we're above that, a long way above that bubble point, because we know we don't have a gas cap and stuff like that, getting good PVT samples is is critical, but it's usually not too bad because we're a long way above our bubble point. But we need to draw that well down enough so that we can unload the fluids and get the fluids to sample if we're separating in a test or if we're cleaning out those fluids. And then there's a number of different types of samples we can do. Bottom hole samples are essentially non-pressurized samples. I've taken a lot of these in my career where they're often used then for the marketing purposes. Are there any, what kind of fluids do we have? Are there any of those other waxes and things that we need to consider at surface? And we can get these, again, they don't necessarily have to be pressurized, and we can get some larger volumes. The two main types of samples that we collect, though, are either surface separator samples, where we collect a sample of our gas and a sample of our oil, and then in a lab, we can tell the lab, okay, well, we know what the GOR is of that, and we know what the reservoir and temperature are, and they can recombine those samples back into a single-phase reservoir fluid in the lab. Can be done very, very successfully, but again, we need to have a really good handle on what that producing GOR is before we've dropped below bubble point, and we need to have a good handle on what our reservoir temperature and pressure are for the lab. And then for the most accurate sampling is we can run downhole tools. So Schlumberger's tools, the modular dynamic tester, the MDT, but there are other available tools through the different service provider. And this allows us, and we can now run these on pipe as well as on wireline, but it allows us to actually put a little canister right up against the reservoir zone that we're going to test and to collect pressurized samples that the lab can take and directly then measure our fluid. So if understanding the fluid is really critical and you're really close to that saturation pressure, so surface samples are going to drop you below your bubble point and your dew point, getting downhole samples is really critical to understanding that behavior. And then once we actually, for our lab test for our black oil, once we actually get those samples, either the recombined separator samples or the downhole samples back to the lab, we want to do a number of different tests. We want to test that fluid composition. We want to understand what that C7 plus is and what our API is and stuff like that of the fluid. We want to do a flash test, which is going to allow us to define that formation volume factor and solution GOR at the different separator conditions. So we're going to have to provide the lab with those separator conditions that we're expecting. We then do a flash vaporization test, which allows us to define the properties above the bubble point, and so how the formation volume factor and viscosity are going to behave above bubble point. And then we do a differential vaporization test below the bubble point to understand as we deplete and that we take those fluids out, how our solution GOR and our formation volume factor and viscosity are going to change as we take that free gas out at different temperatures. And then our viscosity measurements, we do both above and below, and they're usually done with a rolling ball viscometer so that we can actually test how that ball rolls through the reservoir with different temperatures and pressures. And then a point of note is that all of our differential vaporization tests need to be corrected back for separator conditions. We don't produce our reservoirs to stock tank conditions. We produce our reservoirs into separators with known temperatures and pressures. And so that is what we need to understand in order to characterize the fluid and the volumes that are going to end up flowing through our surface facilities. So, to summarize, black oils initially, because of where we are on the critical point and our temperature and pressure, are liquids at reservoir conditions. And at surface, the products separate into stock tank oil and separator gas. And generally, from our characterization for black oils, that initial GOR, that initial solution gas, is typically less than 1,500 standard cubic feet per stock tank barrel, which is always a really good indicator for when we don't have tests or lab data and stuff, and we're just looking at production data to try and understand what kind of fluid we have. When we actually drop below our bubble point, solution gas is liberated in the reservoir and creates free gas in the reservoir. But that solution gas has very little other hydrocarbons that get re-vaporized back as liquids later. So once that, for black oils, once that gas has come out, generally we tend to see then the remaining oil that comes to surface and the gas are then separate streams. And what we see with time is that GORs then increase over time once we drop below that bubble point pressure. So it's hugely critical that we understand what that constant GOR is from our production data or from our lab testing before we hit that bubble point, and that free gas is in the reservoir, and we see that increase in gas with time. It's also really important when we're doing decline curves and forecasting that we also have an idea of how that solution GOR is going, or how that producing GOR, is going to increase with time as well. Because we don't want to keep GOR constant when we're doing forecasts, because we know through phase behavior that it's going to increase with time. If we want to have accurate descriptions of our reservoir fluids, then we really need to go through those standard laboratory tests that can be done for us to understand exactly how that fluid's going to behave with time. But if time and expense or sampling is not possible, correlations can provide an adequate description. But like I said, especially for viscosity, it can be fairly terrible. And it's always worth checking, if we don't have other information, how some of the different correlations calculate, and making sure that the correlation is an appropriate correlation for the type of fluid that you have. So if you want, this is just kind of a sample out of our Reservoir Engineering for Other Disciplines class, specifically about black oil. But if you are interested, and there's some additional classes that cover PVT of gases and of volatile fluids and a little bit more detail about black oil. There's the basic Reservoir Engineering class, the Reservoir Engineering for Other Disciplines, where some of this content's been taken from. The Applied Reservoir Engineering class goes into a lot more detail. And then there's also the reservoir fluid properties in the preparation for reservoir engineering and simulation studies, because these are often very, PVT properties obviously are very necessary to go into any simulation work that we do. And then in terms of some of the individual skill modules that are also online through PetroSkills, the Reservoir Fluid Core and the Reservoir Fluid Fundamentals also have some more information about black oil PVT. So with that, I've seen a couple of questions popping up and stuff like that. I'm happy to hang around. I know we've got about 5 minutes left, but I'm happy to hang around if people have additional questions. And yeah, thank you.
All right, thanks, Deb. Yeah, we do have a handful of questions here, so I'll run through those. And then if others have additional questions, feel free to go ahead and type those in to the chat. One of the questions that came in, I believe you addressed there, that says, in the absence of PVT lab testing, is there a rule of thumb to calculate the initial gas-oil ratio?
So you really need to use your production data. If you don't have production data because you're early in appraisal, and I'm actually working on one at the moment that's like that, it's going to be through analog, unfortunately. Until you either get a fluid sample or have production data, that's not something that correlations is going to give you. So it's really critical, again, to emphasize, super critical that we get fluid samples early in our appraisal stage of our reservoir characterization and field development planning, to make sure that we can get what that solution GOR is, and along with some of the other properties, but solution GOR, to understand how much gas and oil we're going to produce over time, is really critical. So.
Okay, and then a comment came in from a colleague, Stan Kleinsteiber. He says, for simple mixtures, the entire phase envelope can be constructed by repeated measurements in the lab, and that for most petroleum mixtures, PVT tests will measure the phase splits at reservoir temperature with various pressures and at separator conditions. And the entire phase envelope could be calculated using an equation of state tuned to the experimental data.
That's a good point, actually. One of the things that we didn't go into, and I did not mention at all, is then the full equation of state modeling that's done for fluid analysis. So for people that are interested in that, it's definitely something that's definitely not in an introduction class, but it is something that we can use from a characterization point of view, using software and things like that. So thanks, Dan.
Okay. Another question here. To estimate produced GOR, can you just divide the solution GOR by the compressibility factor, Z?
To understand the produced GOR, as we've dropped below bubble point over time, we need to understand the difference essentially between, so we've got total gas production And we need to understand at what point we are in our reservoir pressure cycle and what the current solution GOR is in the reservoir. And then the produced piece, the free gas piece, is just a difference of those. We really need to understand and separate out the free gas portion versus the remaining piece that's coming out of the dissolved, out of the oil, essentially. And I mean, you can measure, if you're forecasting and you don't have production history, this is one of the reasons we use things like reservoir simulation, so that it will calculate how those changes with reservoir pressure will go with time. And then that's also really important if you've got some uncertainty about what that initial GOR is, or other correlations, running sensitivities and tests with how that's going to vary with time. But yeah, if we don't have production data and we're trying to forecast that, it's like I said, that's where using reservoir simulators is really valuable to do that. And there's a number of different, you don't necessarily have to do a full, huge reservoir simulator if you're early on. There's other 2D, sort of more tank style ones as well that will help estimate some of that, or depending on how complex it is, big full field reservoir simulations. So I don't know if that person already has production data or is trying to forecast production data. So depending on where they are in their reservoir life.
Okay. Next question asks if you could describe a little bit the relationship between GOR and density.
Yeah, so I didn't put up the density plots, but again, we're going to see as we deplete our reservoirs, and I assume this is for, I don't know if this means density in the reservoir or just density generally. I'm assuming we're talking about reservoir. Because similar to the reservoir gas oil ratio and viscosity, as we take that gas out, because obviously gas is much lighter than the heavier components, methane's lighter than ethane and subsequently down. So as that free gas comes out of the reservoir fluid, the density in the reservoir is going to get heavier and heavier with time. And it's one of the reasons that we also end up leaving some of that oil behind, because it becomes, the density in terms of its properties won't flow. And it's also in that picture I showed with the very light gas condensate at the surface at the top of the reservoir going all the way down to an oil rim at the bottom. That is a density impact and throughout that reservoir because of how thick it was, because those heavier components want to be at the bottom and the lighter components want to be at the top of that column. So density can vary throughout the reservoir, and in those kind of situations, we would need to understand the gas oil ratio impacts and the way that that reservoir and density is going to change with time throughout the reservoir. That's quite an extreme case in that particular scenario. But yeah, the reservoir fluid will see a increasing density with time as the lighter ends come out as we produce, and the gas oil ratio of the reservoir fluid declines. So.
Okay. Next question is, do you have a preferred correlation to use for black oils? And then are there some that are better than others for unconventional oils?
So I like Baskin bags, partly because I've seen that it generally works on a lot of different types of fluids. But one of the things that I would stress is that we want to try and also match characterization of the actual production performance. If you don't have a lab test, what I've done when I'm building PVT models for reservoir simulation is that we may need to test a couple of different ones so that we can actually characterize how that gas and oil are behaving with time, particularly if you can match your oil, but your gas, you're not, the bubble point's not correct, or you're not getting enough free gas, or you're getting too much free gas, you might need to change the correlation you're using. If you don't have any production history to match to, as is the case with one of the ones I'm using, one of the fields I'm working on at the moment, we've just had to run some sensitivities and look at how the different correlations impact the forecast, and not until we won't know which one's better until we get some samples and some production data to be able to correlate that. But for black oils, I generally like Baskin bags, but it also depends what correlations you have available to you in the software you have. So sometimes we end up using standing because it's usually available in a lot of the different software packages as well. But I can't emphasize enough that we always need to be testing our assumptions and updating them when we get new information. So matching to production history and matching to lab data. In terms of the second question with the unconventionals, the unconventional fluid characterization is especially challenging because a lot of our unconventional reservoirs are not black oil, they're volatile fluids. And usually all we have to go by is early production data. And even from that, it's sometimes really challenging to understand if we're a gas condensate or if we're a volatile oil. And characterizations for those without lab data, even with lab data sometimes because of the challenges associated with getting good volatile fluid samples for unconventionals can be very challenging. So as much as possible when I'm working with clients doing unconventionals, if we're looking at doing reservoir simulation or history matching or understanding some of this, trying to get really good early representative fluid samples from the separator and doing tests in the lab to do recombination is usually the best way to go. But in terms of which correlations to use for some of those, it's challenging because it's much more in that volatile window for unconventionals, not black oil.
All right, and I've got a comment here from James Langer, one of our facilities instructors. He says, for surface engineers, remember the HYSIS phase diagram needs to be tuned to match the core lab's PVT report. He says most engineering companies just import the data from PVT sim into HYSIS, and many projects he's reviewed make this mistake, and the flash gas compression HP is installed in the wrong place. And so the only solution is to reduce inlet capacity. He says, I've seen this error on every project I've reviewed in Europe and the Gulf of Mexico, and he gets called in when the project starts up and they can't meet design rates.
No, I appreciate the comments, James. It's, again, as reservoir engineers and facilities engineers, it's often very easy for us to sit in our own little silos and not talk to each other, but it is super important that we understand the full picture of where the hydrocarbon fluids are going, where they're flowing, and how we're doing some of these corrections for separator conditions and all this other stuff. So it's a really good point. I appreciate it.
All right, and a few more here. While drilling, are there methods to obtain meaningful fluid samples, or are we really only obtaining borehole fluids?
So there has been some recent progress on running both pressure and fluid chambers on pipe. I haven't done the fluid sampling one, but I've definitely done like MDT, more like pressure with depth stuff on pipe. And as long as usually the tools are very similar to the MDT tools and stuff, and they have little pumps in them that will allow you to stop, clean up, and collect fluid samples as you're drilling. One of the issues, and it's always something that you have to work with then your drilling engineers and your drilling team on, is that when you're drilling a well, and you've got all that pipe to then sit and stop and clean and condition the wellbore and then take the time to do the fluid sample often makes a lot of drilling engineers very nervous because of differential sticking and getting stuck. So again, it's understanding, if there's any depleted zones that you're going through, if there's any issues in terms of sitting there to condition the well with the little tool that can be run, it is more of a concern. But yeah, we are starting to see the ability to run some of these tools on pipe as we're actually as we're drilling wells. The only thing I would say is that particularly still for our volatile fluids, or if we don't know what the fluid is, it might be better to go back in and once we've drilled the well and clean up and do the analysis and then design the plan so that we're not drawing down below bubble point or dew point and that we're collecting representative samples instead of spending the money blind to just kind of go in and do it. But I have some experience running stuff on pipe to collect pressures really successfully. And it's just a matter of, again, what are the objectives of the test? Is everybody on board with that? And then working with the drilling and completions engineers to make sure they're comfortable to sit and spend the time cleaning up and collecting those samples. So.
All right. Next question is, where do we classify fluids with GOR above 1,800 cubic feet per barrel?
So I popped up and I stopped sharing. I'll go back to the slide with this particular slide is the one that I need. Let's go back. Can you see that again, Clay?
Yeah, it's popping up now.
Yep. So something at 18,000 we would put into more of a wet gas kind of classification, which is where we should be seeing that the reservoir fluid is still going to be coming up as 100% gas, and that we're not seeing that fluid separation until we hit the separator at surface. But you can see as well, these are only indications. So 18,000 might still be a gas condensate, but really one of the things you're going to want to understand then is your C7 plus components with that. If your reservoir fluid, and again, it's really important that we recombine, if we're doing surface samples, the gas and the oil together from that separator, because if we're just doing the gas, we're going to be leaving that liquid that was part of that reservoir fluid out. But that C7 plus piece is then going to be really critical in helping sort of differentiate that. And really at the end of the day, understanding then because this is going to be a very gassy reservoir, obviously, but if maximizing liquids is the value driver, working with the production teams and the production engineers and the reservoir engineers to understand how the fluid is going to change with time. Because if it is truly a wet gas, we should stay as single phase gas throughout the reservoir, throughout the life of the reservoir. If we've actually dropped, if it's closer to being more of a gas condensate, we risk dropping below the dew point in the reservoir and dropping those liquids out in the reservoir versus in the separator. So it is sitting right on that margin and that border of that, but that's where getting, again, representative samples to really understand that phase behavior. And if you're going to hit that dew point during the life of the reservoir, it's going to then change how you manage and develop that if maximizing liquids is key. So, but based on this, I would say it's wet gas, but it's close. So these aren't hard and fast rules, but they're good indications. So.
All right, and then the last two here, are black oils frequently found to have a gas cap in never drilled reservoirs?
So it just depends on what the initial reservoir pressure is. I've worked on both throughout my career. It's just something that we need to be really careful of. So if we're a long way above the reservoir, if the reservoir pressure initially is a long way above that bubble point, then we won't find a gas cap initially. And there's still a lot of fields that I've worked on in the recent years that are like that. But if we do find a reservoir that has a gas cap initially, one of the things that we need to be really careful of when we're setting up our initial characterization, when we're talking to the lab, is that saturation pressure and that reservoir pressure need to be, they are the same then, because we are at equilibrium in terms of the free gas and the oil. So it's not that it's one more than the other, but it's really, because I have seen it before where we've got lab reports back and the bubble point has been said to be higher than the reservoir pressure, but we know that we have a gas cap initially. So it's not possible. It has to be at that bubble point, and that initial reservoir pressure has to be in equilibrium. And that's really the main key with how we find our reservoirs initially. If we've got a reservoir where that initial pressure is a long way above bubble point, the thing that's nice about that is we have a lot more drawdown that we can play with when we're producing our reservoirs until we hit that bubble point. So we can draw our wells down harder and for longer before we start to liberate and see all that free gas coming out of solution. So it really comes down to then our reservoir management and how we then manage those reservoirs over the producing life. So.
All right, and then before I get to the last question here, I had a number of questions come in asking if they could receive copies of the presentation. We are recording this session, and so we will make that recording available to you with the presentation. It'll probably take a day or so to process, but we will definitely send that to everybody on the call, as well as ones who had to drop off early or signed up but then couldn't make it, if you have any colleagues there. So yes, we will be sending this out. And so the last question here is, how does separator pressure affect reservoir performance?
So again, it really depends on what the objectives of the reservoir are, and how the fluids are going to change over time through that separator. So for gases, we want to draw the pressure down as low as we possibly can, and even for our wet gases, if maximizing gas production is the objective, but if our separator pressure is high, then we're not going to be able to draw that down. In terms of oil reservoirs, again, we're wanting to make sure that we can get the separation at surface that we need. We might also be chasing certain specifications on our oil, and depending on how we draw down and change separator conditions, it's going to change how much free gas we still have in that oil, versus if we were to draw all the way down to stock tank conditions and stuff like that. So depending on how the separators are set, how many stages of separation we have, really just depends on how much dissolved gas we still have in that oil as it flows through the system. If there's facilities constraints in terms of how much gas can come off as it's changing, then we might want to have lower separator pressures and temperature, or separator conditions, versus higher. But it really comes down to working with the facilities engineers, the design of the facilities, and how much gas and liquid the different parts of the separator, the different parts of the facilities can handle, and how that's going to change with time. So.
All right. Well, Deb, thank you very much for an awesome presentation and all the good Q&A.
Yeah, I appreciate all the questions and the participation from everybody. So, yeah, thank you.
And thanks, everyone, for joining us. Again, just a quick marketing plug. We do one of these every Tuesday, so make sure and go out to the website. I will send you, when I send the recording, I'll send the upcoming schedule. And we hope you're able to find something that interests you and take advantage. So everyone, have a great rest of your Tuesday, and stay safe and take care.
Thanks, Clay. Thanks, everyone.
All right. Bye all.